Hello, welcome to this video. So in this video we're going to be talking about whether there is a crisis brewing at the heart of physics, and this is inspired by some physicists like Sabine Hossenfelder talking about the problems of academia and the problems with ideas like string theory, and also inspired by videos of some other physicists, particularly Carroll, indicating that perhaps actually there isn't anything too bad happening at the foundations of physics. So with so much discussion, with questions around are physicists making theoretical predictions in terms of the foundations of physics that can actually be verified, does science need to be able to give falsifiable statements? Is falsifiability a core aspect of science? All of these ideas are worth discussing because we are at an unprecedented time in physics where in some fields we have models which are so good it's very hard to know how to progress with the field in a way that experiments can actually keep up with, because our models work so well to explore new physics. It feels like we have to go into some very wild directions, and in other fields they're very young, like cosmology, and we're just beginning to understand the universe. So it's worth asking, is there a crisis at the heart of physics? Well, let's firstly be very clear on what parts of physics there may be a crisis in. Because physics is very broad, and experimental physics, so physics involving the properties of materials, like many of you will have heard of the material graphene, and so material science is doing really well. People involved in kind of atomic physics and optics are looking at the metamaterials, which interact with light in very unusual ways. Physicists are looking at lasers, and lasers have a wide variety of applications. Physicists are looking at things like code, but code that might make use of existing quantum computers. So clearly not all of physics is in a crisis. However, some parts of physics do seem to be fundamentally struggling. And a natural question is there a crisis in these fields? Now it's worth saying, just to clarify, I am not an expert in the two disciplines of physics I'll be talking about, where I think there may be crises of different kinds. However, no one is an expert on an entire field of physics anyway, and also this is a channel where I think it's important to discuss the nature of physics and humans doing physics, as well as the equations themselves. The practice of physics is, just as important as the fruits of physics, because what's happening in physics influences what we learn about our universe. So we'll start with particle physics. Now, low energy particle physics is not in any difficulty. And by low energy particle physics, I really mean using ideas in particle physics such as renormalization, such as quantum field theory, to look at things like solid state physics, perhaps even atomic physics, but essentially materials that we can make use of, that we have accessible in our everyday life, where we're not really worrying that much about the behaviour of the fundamental forces of nature in a very general way. So, you know, in low energy physics, we're more concerned with how do large groups of particles interact, to put it fairly crudely. Whereas in high energy physics, we're going, well, we've got this brilliantly successful model of all the particles that we are very confident exist and have experimental confirmation exist. And these particles are the quarks, the leptons, and the force-carrying particles. And high energy physics goes, well, are there any other particles? So if we take this standard model, which we tested to some energies, and we've got confirmation that we're on the right grounds, if we take this model, how should we extend it to really high energy levels? Would new physics emerge? What would that look like? Would there be new particles? Would there be new types of forces? Would particles behave in an unusual way? Would forces start to become even more unified? Now, I would say, to the credit of high energy particle physicists, they have a tough job. And that is because when the Large Hadron Collider first turned on, physicists were hoping it would discover loads of particles that we weren't too sure if they existed or not, but many physicists had high hopes that they would exist at higher energies. So ideas like supersymmetry were very popular, but we didn't find any supersymmetric particles. In the second string revolution, I think in the 1980s, there was excitement around particularly extra dimensions, and people hoped when the Large Hadron Collider turned on that we might find evidence that there are higher dimensions. People were looking at the behaviour of gravity at really, really tiny distances. Not quite the distances we would expect quantum gravity to occur, but at small enough distances that perhaps we could learn something about gravity decreasing or increasing in a way that would be inconsistent if there were only 4 dimensions of space-time. But there were lots and lots of things we hoped that the Large Hadron Collider would see. It saw none of these things. The only thing it saw was the Higgs boson, and there was pretty much unanimous agreement that the Higgs boson existed. In fact, there was so much unanimous agreement that it existed long before we detected it that the Higgs boson was considered to be part of the standard model even before we really had evidence to justly put it in with all of the other particles in the standard model. Instead, what the Large Hadron Collider did is it showed, by giving us many particle interactions of a large variety of nature to analyse, it showed that the standard model worked really, really well. It made excellent predictions in great agreement with observation. So that's a massive win for experimental physics, but theoretically it's a disaster because the standard model is doing so well. There is essentially no experimental data to use to allow us to work out what might be good extensions of the standard model. Now, a fairly pragmatic view one can take is that, well, perhaps, therefore, we should not worry about extending the standard model. Perhaps we're in a period where, given we have no evidence that the standard model breaks down at energies we can easily access, perhaps we should just leave the standard model as it is and put the money we would put into high energy physics into other areas of fundamental physics. I believe, and I could be mistaken, but I believe that this is the view that a female physicist, I think originally from Germany, called Sabine Hossenfelder holds. And here is an image of Sabine Hossenfelder. Now it's worth saying in this video I will be referring to what I gather about her ideas as well as what I gather about another physicist's ideas. But it's always a dangerous thing summarising somebody else's view, so please take everything I say about other physicists' views with a grain of salt. But anyway, Sabine Hossenfelder, as far as I can infer, seems to have a very pragmatic view with physics, including high energy particle physics. I think, and to be fair, I can see her point. I mean, it is quite concerning when high energy particle physicists want to build an even larger particle accelerator that will cost tens of billions of dollars. And their main justification are twofold. Now, the first reason I kind of get to study the Higgs boson in more detail, because the Higgs boson is a very unique kind of particle. I believe it is described by a scalar field, so it's a scalar boson, and those parts we haven't actually seen another scalar particle before, so that's quite exciting. But the second reason high energy particle physicists give to build an even bigger particle accelerator is that we might, and the key word is might, discover lots of new wonderful bits of physics. But, well, particle physicists said we would discover them when we built the LHC. Did we discover them? No. So I think we have a right to be very sceptical, and I heard another physicist, I can't remember his name, but this is a string theorist who remembers the development of string theory and knows people like Ad Whitton. This physicist was saying we have to be fair to people, that people are going to be sceptical about string theory and other things. Mainly because people were so sure we would see something when the LHC turned on and we didn't see any of these wonderful, what seem to be imaginations of particle physicists. And that leads to a bigger problem in the foundations of physics, that without experimental evidence, theoretical physics is very much left to its own devices, where the only guidance really is what is aesthetically beautiful or what seems most natural to the people at the forefront of their fields. But things like beauty, naturalness, these things are very subjective and very personal, and a very poor way to tell if a theory is good or not. I'm personally of the view that we cannot do science properly unless we have new experimental evidence to work with, because it's experimental evidence that is the objective backbone. I mean, it's a backbone that we can reason about fairly objectively of physics. And without it, we start making mathematical fantasies. And I think one problem with string theory is it was a mathematical fantasy with the hope of describing all of the universe and deriving many constants by thinking about particles, and therefore ultimately force-carrying particles, as strings, so truly one-dimensional objects. rather than point particles, and that the tension of a string could produce all the other constants in the standard model, such as the mass of the electron. It might even tell us something about the mass of the neutrino, something experimentalists have found an upper bound for, but we haven't actually got the value of the mass of neutrinos. We just think they have mass because of neutrino oscillation, which I'll make a video about at some point. But as it happens with string theory, a problem arose with string theory. Well, one, that they needed more than the 4 dimensions of space-time we can currently observe, and that led to the idea of compactifying dimensions, but it turns out that actually there are many ways to compactify the dimensions, and so we don't actually know what compactification we should be looking for, making it very hard for string theory to give any concrete statements about what experimentalists should or shouldn't observe if string theory is true. But on top of that mess, it turns out that if you want to unify the forces and everything in string theory, you seem to be in a land of string theory which conflicts with experiments, and there's a way around this. And the way around this is to actually go the tensions of strings as not a fundamental constant but a dynamical variable. But then that means that we can't predict all other constants just from a fundamental constant of the tension of the string. So the beauty of string theory in terms of predicting fundamental constants from a single constant goes away, because that single constant is no longer a constant. But anyway, I think when physicists start creating mathematical fantasies, it's rather troubling when, upon seeing that the universe doesn't satisfy those mathematical fantasies, instead of ditching the theory, they change the theory, which adds even more problems and pulls the theory even further away from its original goal of describing reality. But I think that is partly inevitable when you do not have experimental data to fall back on. But there's another crisis emerging, and this is a crisis within cosmology. Now, unlike with high-energy particle physics, I think the crisis, and I should really say crises in cosmology, is really good. Because with cosmology, the thing that is triggering the crisis isn't that made-up mathematical universes don't seem to agree with reality. The problem with cosmology, well, problem for want of a better word, is that experimental evidence is showing us that models we had in the past, like the Friedmann-Walker metric to describe an expanding universe, and assumptions about the distribution of matter in the universe, like it being isotropic and homogeneous, these assumptions might actually be false, or we have good reason to believe that these assumptions are false. I mean, cosmologists are finding regularly now structures that are far too large for the observable universe, at least to be sufficiently isotropic and homogeneous to work with the models they've traditionally had. Cosmologists have found that many galaxies, far from just getting further away from us, many galaxies seem to be moving towards some location, and we don't know why they're doing this. We say that they are moving towards the Great Attractor, but we don't know what the Great Attractor is. And that's to say nothing about the persevering mystery around why there seems to be dark matter, where there seems to be dark energy, what dark energy could possibly be. I mean, recently they've started wondering whether things like the cosmological constant, which is usually considered to relate to dark energy, even though one can even question that, but scientists have begun proposing that maybe the cosmological constant is not actually a constant. Maybe it's a dynamical variable. Now that might sound similar to what string theorists did with the tension of the string, with promoting that to a dynamical variable, but the difference is we don't know if string theory is true. There is no experimental confirmation that string theory is true, whereas with cosmology we are getting a flood of evidence and experimental data. And I'm personally really hoping that the money that sub-scientists want to go into this new big particle collider doesn't go into another particle collider, but goes towards cosmology, because we are finding tons of new information very regularly. It is a very exciting area of research. So I think cosmology is in a state of multiple crises. And that's to say nothing about related fields like galactic evolution, because scientists have seen that galaxies seem to form very early in the universe, far earlier than was thought to be possible. Similarly with supermassive black holes, and scientists have even begun going, well, if they formed so early, then there must have been tons of stellar activity early on in the universe. But looking at that stellar activity, it seems that that would create radiation that would enter a thermal equilibrium, and that radiation could be what we call the CMB, cosmic microwave background radiation. Now, we used to think, and I think most physicists still do think, that the CMB is a relic from the Big Bang. But maybe it's just a relic from incredibly active star formation in the very early universe. Meaning that the Big Bang might not have happened 13.7 billion years ago. It might not have happened at all. And if it didn't happen at all, then maybe these galaxies that we think formed very shortly after the start of the universe, on a cosmological timescale at least, maybe they actually had loads of time to form. So, you know, we're questioning so much in cosmology. It's quite wonderful. So cosmology is breaking so many models, so many ideas that physicists have. But it's happening because experimental evidence is forcing us to question and refine our models. And that is a brilliant state of crises to face. That's what we want to happen in an ideal world. But, you know, one physicist that is currently working in cosmology is a physicist called Carroll. Now, Carroll wrote a beautiful book on general relativity called Space-Time and Geometry. If you're very mathematically minded, I would recommend that book. It's really beautiful. Definitely some sections are for the pure mathematician. He really likes talking about maths in great technical detail, such as rigorously defining the concept of a metric, dual vector spaces, and so on. But in relation to physics, Carroll doesn't think that there is really a crisis going on in the fundamentals of physics. And I would just say that, for me, he just comes across as incredibly patient. And I'm not sure if I'm that patient. In that, Carroll seems cool with the idea of scientists taking hundreds of years, potentially, to answer some of the questions that is being researched. Questions around the holographic principle and other things. And, you know, to be fair, the questions we're asking are naturally deeper, are naturally more far-reaching, and are naturally more abstract and therefore in many ways harder to test than previous ideas. So perhaps the progress of physics should be expected to slow down, and we should be more lenient with how long we expect to wait till we get experimental tests of our theoretical ideas. However, I think given that there are projects that could potentially be tested in the very near future, we should prioritise these projects with promising results in the near future over, you know, ideas like string theory, which might take thousands of years before we can ever hope to directly or, you know, conclusively test. For example, Sabine Hossenfelder works a lot on the fundamentals of quantum mechanics. She's very interested in the measurement problem. She has a video on her channel on decoherence, and why she feels decoherence doesn't solve the measurement problem. It's debated whether decoherence does or does not. I would highly recommend checking out both their channels, and in the link below this video you can find videos of both Carroll and Sabine Hossenfelder being interviewed about their respective views on the state of physics. But I would like to finish by just mentioning that I think the word crisis, when it's being used to describe physics that isn't growing, so for example, physics related to high energy particle physics, I think crisis might be the wrong word. Because really what's happening with these kinds of areas like high energy particle physics is we are in an experimental wasteland. It is arid. There is no experimental rainfall we are expecting for a very, very long time. So the questions in these areas, such as string theory, in my personal opinion, no longer are under the umbrella of physics. Instead, they are under the umbrella of philosophy. We are doing metaphysics when talking about string theory. We are talking about a speculative idea about how the universe might work, what it might be made up of, which is outside of our current abilities to test. So when I say high energy particle physics is in a state of crisis, I mean it is transitioning from an area of physics to one of philosophy. And Carroll, I believe, has wrote papers both in physics journals and in philosophy journals. Although I might be getting him confused with Brian Greene there, but Brian Greene is Brian Greene is a string theorist, but I'm pretty sure that's the case, and it's definitely is happening in the foundations of physics that some research has been published in philosophical journals. And I personally believe that's because some parts of what we traditionally called physics that may well once have seemed testable, like string theory, when we turn the LHC on, is really now an area of philosophy. So I think philosophy has got some really exciting stuff to look into. And I'm very excited to see string theory explored as a philosophy. And I think philosophy is just as important and profound as physics, just in different ways. So that's my kind of outlook on the current state of physics. We have wonderful experimental progress leading to wonderful forms of crises in cosmology, making it a really active field, whereas some other parts of physics like high-energy particle physics, is producing lots of ideas that are becoming more and more part of the stage of philosophy. And therefore, essentially, we find in that realm ourselves in the position of the ancient Greeks. Just as the ancient Greeks once asked, do atoms exist? In fact, the word atoms comes from the Greek word atomos. And there was a lot of debate whether atoms truly existed. Aristotle believed they did, Plato believed they didn't. Now we are in a similar situation with string theory. We are asking, do relativistic quantum mechanical strings describe the particles in the Standard Model? And one day it might become a scientific question again, but for now we are free to question it as philosophers. So I hope you have a good week ahead, a brilliant morning, afternoon, evening, or night, whenever you may be watching this video, and I look forward to seeing you for some more wonderful physics soon.